Hello ladies and gentlemen, I am Dr. Claudia Albers, Planet X research and professional physicist. And today I'd like to bring to you another one of my articles. This one is entitled Planet X and the A Spacecraft Solar Wind Simulation. Now recently Owen Steiger noticed something strange in the solar wind simulations derived from the ACE, which stands for Advanced Composition Explorer spacecraft, which is in the L1 Lagrange point and is designed to provide advance warning of CMEs and other energetic solar wind events impacting the Earth's magnetosphere. And we see here where the L1 Lagrange point is, so that places the spacecraft directly in line between the Sun and the Earth. So whatever CME comes from the Sun will impact the spacecraft first, and thus it will be able to provide advanced warning to Earth as to it impacting the magnetosphere. Now, Wayne noticed that since June, one of the simulations, the one showing the position of the magnetopause, which is the boundary between the Earth's magnetosphere and interplanetary space, was showing much darker than normal regions. And we see that in this image from June 6, 2018. And this white line here indicates the magnetopause position. This black and white circle is the Earth. The white part means that this is the Earth side. So the Sun would be here, the solar wind comes from this side. This is the geosynchronous satellite orbit. And usually we have the highest density, and the density is indicated by the scale here. Usually it's along the magnetopause. Sometimes a higher density occurs on the night side as particles come in from the night side after having impacted the magnetosphere. But usually the highest density, as we see in this image, is along the magnetopause position. Now the density does vary across the region under simulation, and we usually have the lowest density, and this is actually current density, but because these are charged particles that are coming in the solar wind, it's basically the same as density of particles. And this means that we would have a variation. There would be some region or some point somewhere that would have the lowest density reading for a particular frame of the simulation, and there would be a region that would have the highest, and that would provide what is placed on the scale. So in this particular scale, we have the lowest density that was simulated to have occurred in the region under simulation was 0.00004, and the highest was 0.01704. And in this one, we have the lowest was 0.0001. Now notice that the lowest here ends in a 1 and the lowest there ends in a 4. So we actually have the lowest here being higher than that one. And the same thing seems to be occurring with the maximum. So we have here a maximum density of 0.01704, and the maximum here is 0.01198. So this is a lower maximum than there. But the colors are assigned so that we have a dark blue for density which is lower in this diagram than this purple, which is assigned to this number ending in 4. So when we first look at the diagram, we see purple, we tend to think that we have lower densities in this image than in that image. But we actually have the opposite, because the color purple is assigned to a minimum density which is higher than the minimum density here. So a purple color here is actually means a higher density than what the blue color in this diagram means. So we cannot just compare diagrams according to color. We actually have to look at the scale. Now we can also calculate what the variation in the density is. And we can see that the variation here, we just take this value and subtract that value. So on this side is just 0.017. So we have a variation of 0.017 across the different densities in the region under simulation for this side, the left side image. And for that one, we have 0.01198 minus that value. So the variation is 0.01197. Now, you will agree that this is a lower variation. So this seems to suggest that more colors may be used when the variation in density across the region of simulation is higher. But that is not actually the case, because if we look at the image here that we have here, which is from June 30th, and we compare it again with the one we had here on the left, so it's the one from June 6th, and we look at the scales again, the lowest number on the scale is now 0. So you see it ends in 0. So this is absolute 0. And here we have a number that ends in 4. So we have a higher minimum density in this image than in that image, but the same color is assigned to that minimum value. Okay, that's not too much of a problem. It means that they introduced a new color for minimums. But then if we look at the red, which is the maximum densities, we see that the highest density here is 0.00761, and the highest here is 0.01704. So this 0.0761, which is the maximum value here, is much lower than this value here. You can see I have 2 zeros there and only 1 0 here after the decimal point. So this is a much higher value than that one. And so we have a much lower variation in this image. The variation over here would be 0.00761. It's the total value because that's a 0, whilst here it's 0.017. We have a much wider variation here, and yet if you look carefully, actually there are darker colors assigned to the extremes. So we have a darker red assigned to a maximum value that is actually much lower than the maximum value here, and we have a paler, more orangey red assigned to a maximum value which is higher than there. So this means that if we were comparing these images and we were looking at the color, we would look at this one and we would see some red there. We hardly see any red there. We would tend to think that there's higher density at the magnetopause in this diagram, higher than in this diagram. But that's not actually the case. It's actually the other way around. We actually have higher density here at the magnetopause, and we can see that we have, because this would be the point where we would have the maximum density occurring. There's nothing coming in from this side in this one, and a paler red is assigned to that. So the way these colors are being assigned is counterintuitive, first of all, and they actually seem to imply that there's an effort that has been made to hide higher densities, because that's what it tends to do, that you tend to think that when there is a higher density, when there is higher density, there's actually lower, and when there is high, there's actually lower. So first of all, it's not possible to simply compare density directly through comparing coloring on different simulation images. The scales have to be looked at first. However, the assignment seems to purposely make the occurrence of a higher density at the magnetosphere seem to be lower than it actually is. Thus, the appearance of a darker color in June may indicate that current density is increasing and the programmers are making an extra effort to hide that fact. This would then indicate that increased current density is now arriving from the sun on a regular basis, and an effort is being done to hide it. And a similar thing, a similar situation is occurring with these solar wind speed diagrams, which also show particle density. So again, the same thing, we have a scale here. We have the maximum occurring density in the simulation at the top and the minimum at the bottom. And here we have, we can see some purple has been assigned to this number of minus 0.645. And this is the image from, an image from June 1st, 2018. This is from May 31st. Now, so this dark purple is assigned to minus 0.645, but if we look at the scale here, there's no dark purple, there's only a dark blue. That's the most extreme minimum color here, but it's assigned to a lower density because minus 0.90 is lower than minus 0.645. And then with the maximums, we have a dark red being assigned to 1.330, and we have a red that's not as dark assigned here to 1.97, a much higher density on this logarithmic scale. So if we were to look at the diagrams using color, you would tend to think that you have a wider variation and much higher density at the magnetopause here, because it's darker red. But in fact, the opposite is so. It's just that a more orangey red has been assigned to a much higher density on this diagram. So a lower variation in the color difference actually indicates a higher density at the magnetopause and a higher variation, because if we look at the variation in the densities in this simulation here, we have 1.330 to minus 0.645. So that variation is 1.975, whilst the variation here between minus 0.90 and 1.97 is 2.87. 2.87, so that's, I have it here, 2.87 in the lower diagram, 1.975 in the upper diagram. So we have a much higher variation in densities in the lower diagram, but we have less variation in the colors assigned. So this is definitely counterintuitive and confusing, most likely purposely confusing, because people comparing the colors would seem to think there's a wider variation and higher density at the magnetopause in this diagram than in that diagram. So we seem to have an illogical pattern in assigning colors on the scale. And this seems to, I believe, be done on purpose and in order to subtly hide what is really going on. So the introduction of darker colors into the simulation scale for current density in the June simulation diagrams for the magnetopause position, which was the first shown in the first figures 2 and 3, seems to indicate an increased effort to hide an actual higher particle density at the magnetopause, which would indicate a higher density of charged particles arriving at the magnetosphere as part of the solar wind. This would indicate that the sun is releasing more charged particles, which then become a part of the solar wind rather than less, even though it seems to be in a weakened state and emitting low intensity light. And you may look at article 225 entitled Weakening Sun Source Radiation Measurements on Not All Solar Radiation for more details. Now, as the Planet X system of stellar cores continue to draw energy from the sun, it is likely that the intensity of light emission decreases. This is observed in the SDO images, which I show in this article. The normal solar wind mechanism would also tend to decrease, leading to a slower moving solar wind, which we seem to be observing more often. However, there may be a direct release of plasma from the sun's outer layers, which would join the solar wind and thus increase the density of the solar wind. as there would be more particles in the solar wind. This would occur as a result of the sun losing gravitational influence, which would cause it to start losing its hold on its outer layers of plasma. This seems to also be the reason why a star would turn into a red giant as it ages. It loses its hold on its outer layer, which then drifts off as increased solar wind, but at lower velocities than normal, as the normal forced ejection would decline in strength as the star loses its ability to generate energy in its core. And you may look at Article 184 entitled Stellar Core Evolution for more details on that. In conclusion, darker regions in the simulation diagrams for the magnetopause position are due to a color assignment change, which actually seems chaotic and designed to hide what is really going on. The introduction of a darker color actually seems to be an additional effort, which is being done to hide the fact that higher particle density may be arriving at the magnetosphere. This would go along with the fact that the sun is increasingly weaker due to the draining effect of the Planet X system of stellar cores, and would thus tend to release its outer layers of plasma. This is Dr. Claudia Albers, Planet X physicist. Thank you for watching.